All right, let's get right into it. We all use encryption constantly, every single day, right? But have you ever stopped to think about how it actually works? How does some abstract math concept, a secret, actually turn into a physical thing, like something that can flip a switch or lock a door? Well, that's the exact journey we're going on in this explainer, from the pure logic of keeping secrets to the actual volts and amps flowing through a real-world circuit. So, here's our roadmap. We're going to start with the big idea, the unbreakable math lock. Then, we'll get into the clever clock math that scrambles numbers. After that, we make the jump from logic to light, from true and false to actual voltage. Then we'll get our hands dirty with the language of circuits themselves. And finally, we'll pull back and look at what this all means for the future of trust. Okay, so first things first. The absolute core challenge in all of cryptography is building a one-way street. We need to create a process that's super easy to do, but next to impossible to undo. Here's a simple way to think about it. Imagine mixing two colors of paint. Super easy to do, right? But now, what if I just hand you the final mixed color? Could you perfectly unmix it? Could you tell me exactly which two original shades I started with? Of course not. It's a one-way street. That original information is gone for good. And believe it or not, that's exactly what we need our math to do. And that's precisely what a trapdoor function is. It is the perfect mathematical version of mixing paint. It's engineered to be a one-way process, with one critical exception. You see, it's almost impossible to reverse unless you have a secret key. That key is like a secret instruction that opens up a hidden trapdoor, letting you get right back to where you started. So this is it. This simple contrast between easy and hard is what powers pretty much the entire modern internet. For a computer, multiplying two gigantic prime numbers together is a piece of cake. It happens in a flash. But trying to take that massive resulting number and work backwards to find the two original primes, well, that is just brutally, mind-bogglingly difficult. The security of your email, your online banking, it's all riding on a bet that this problem stays hard. So how in the world do we actually build one of these mathematical one-way streets? It turns out we use a concept that's beautifully simple. In fact, you already get it, even if you don't know its fancy name, modular arithmetic. Yeah, this is literally clock math. If it's 10 o'clock right now and we add 4 hours, you don't say it's 14 o'clock, right? You say it's 2 o'clock. The numbers just wrap around once they hit 12. In math, we call that doing a modulo 12. All we're doing is keeping the remainder. And this simple act of wrapping around changes everything. And wow, this just shows it perfectly. Look on the left. A regular function, y equals x squared, gives you that nice, smooth, predictable curve. You can see the pattern, you can follow it. But on the right, we take the exact same function and just add that little modulo operation. And poof, the pattern is completely gone. It looks like random static. It has completely scrambled the information. You see, the whole point here is that information is lost. If I tell you that I did a mod 12 calculation and the answer was 2, you have absolutely no way of knowing for sure what number I started with. Was it 2, or maybe 14, or 26, or 38? It could be an infinite number of possibilities. And this ambiguity, this uncertainty, it's not a bug. It's the entire feature. It's the mathematical curtain that we use to hide the secret. Okay, and now for the really cool part. We've been hanging out in the world of abstract math. But how does a computer, a physical machine made of silicon and copper, actually do any of this? How do we take these scrambled numbers and make them do something in the real world? This is how pure logic becomes actual electricity. Well, it all starts with incredibly simple rules, like this one. This is a truth table for what's called an AND gate. It's a basic logical blueprint. The rule is simple. The output is only true if input A and input B are both true. Otherwise, it's false. This is one of the most fundamental building blocks of how a computer thinks. And here it is. This is the magic bridge between the abstract and the physical. Inside a computer circuit, the ideas of true and false get a real, physical, measurable meaning. True simply means turn on the power. Apply a high voltage, say 3.3 volts. And false means turn off the power. Apply a low voltage, or 0 volts. That's it. A logical concept is now a physical electrical signal. So check out how this chain of command works. It's actually pretty straightforward. First, you've got your crypto algorithm, right? It does its number crunching and spits out a true. The software sees that and goes, okay, true means high. It then sends a command to a specific little pin on the chip. This is called a GPIO pin, by the way, which just stands for General Purpose Input-Output. And bam, instantly that physical pin starts pumping out 3.3 volts of electricity. Just like that, the abstract math is literally controlling the physical world. So, great. We've made a physical signal. But what are the rules that govern that signal? Now we have to step out of the clean world of pure math and get our hands dirty in the world of physics. We have to understand the fundamental laws that tell electricity what to do. And the absolute king of all these laws is Ohm's law. V equals I times R. Voltage equals current times resistance. Now, this isn't just some dusty formula from a textbook. No way. This is the rule that lets us build hardware that doesn't, immediately blow up. Let's say that 3.3 volt signal we just made is supposed to light up a little LED. If we just hook it up directly, poof, that LED is toast. So we use Ohm's law to figure out the perfect resistor to put in the way to control that flow of current. It's all about making sure the physics works as planned. And right on its heels is the power formula. P equals I times V. Power is simply the current multiplied by the voltage. This is huge because it tells us exactly how much energy our crypto chip is using from one moment to the next as it's doing all these calculations. It's a direct measure of how hard the chip is working. But this actually creates a really sneaky problem. What happens if the very act of doing the math leaves a physical fingerprint? I mean, what if the amount of energy the chip is burning changes in tiny but predictable ways depending on the secret key that it's working with? Well, this is a massive real-world vulnerability called a side-channel risk. An attacker doesn't even have to try and break the fancy math. Instead, they can just hook up some sensitive equipment and watch the device's power consumption. Those tiny little flickers and energy use as the chip crunches the numbers can actually leak information and betray the secret key. The physics of the circuit can end up undermining the math. And this is where the rubber meets the road. It's why we have to actually debug the hardware with a tool like a multimeter. A multimeter is basically our truth detector. We use it to verify that physical reality is actually lining up with what the math says should be happening. So we'll literally touch the probes to that GPIO pin. Are we really getting 3.3 volts when the software says true? We'll measure the resistor. Does it have the right resistance that Ohm's law told us to use? Is there a short circuit somewhere, a path of zero resistance where there shouldn't be? We're literally confirming that the world of physics is listening to the commands from the world of logic. So let's zoom back out for a second. We've traveled all the way from prime numbers to voltage on a wire. What does this incredibly deep connection between math and physics really mean for our future? The thing is, this whole system we've just walked through, it's all built on one giant collective bet. The bet is that certain problems, like factoring those huge numbers, are in a class of problems that are fundamentally hard for computers to solve, even though checking the answer is easy. This is the famous P versus NP problem. If anyone ever proves that these hard NP problems are actually easy P problems, well, our entire global system of encryption would basically shatter overnight. And there is a very real storm cloud on the horizon. It's called Shor's algorithm. It's a theoretical recipe designed to run on a quantum computer, and it can solve that hard factorization problem easily. It would basically take our unbreakable problem and toss it into the easy-to-solve bucket, completely breaking all our current encryption. That is why you hear this constant buzz about the race to create post-quantum cryptography, brand new math that even a quantum computer can't crack. And all of this brings us to this final, really powerful idea. Everything we've talked about, the trapdoors, the clock math, the logic gates, the voltage, it's all about building a system of truth that doesn't depend on anyone's opinion. It's not about trusting a person or a big corporation. The math itself provides the proof. Authenticity stops being a feeling and becomes something you can calculate, something you can verify yourself. It becomes a computed property of the universe that we can all agree on.